In section 5.1 in Calculus BC, we are really making a huge transition in the course. Really, Calc AB is broken up into differential calculus, that has involved the derivative. We are now moving into something called integral calculus. And we haven't even defined the integral. We're not going to do that for a little bit. But you can see our learning target at the top of the notes here. I can approximate area under a curve with three methods: LRAM, RRAM, and MRAM. And that will stand for the left rectangle approximation method, right rectangle approximation method, and the midpoint rectangle approximation method. What we're going to see is that there will be an X partition. We're going to have an X inequality, so to speak. The closed interval from A to B means that X is between A and B, allowing X to equal those endpoints. We're going to take that X interval right there and break it into sub-intervals. So that interval is broken into N different pieces, all the same length today. And they will be really bases of rectangles. We're going to make N rectangles. And the little segments, those subintervals on the x-axis, will be the bases of those rectangles. Now imagine if I were to tell you that we were going, say, from 1 all the way up to 4, just so that we had something to speak of. And if I told you that we were going to make, 3 rectangles, you could see very easily that, we'd go from 1 to 2, 2 to 3, and 3 to 4. I think sometimes it's pretty evident, what the bases of rectangles would look like. But let's just say I decided to make 6 rectangles or another one. If you really think about it, you'd say take that whole interval length and divide it by the number of rectangles that you'd like to build. That's what we're going to see with delta x right here. Delta x is going to be the length of the interval, b minus a, but then we're going to divide by how many rectangles we'd really like to create here, how many subintervals we'd like to have, and that's going to let you know how much delta x should be increasing. So the area underneath the curve can be found with 3 different methods. We've got LRAM, the left rectangle rule, the left rectangle approximation method. You can see this sigma right here. We'd write L sub n. The sigma means sum. And we're going to have a function, f of x times delta x. Delta x was the base of the rectangle. F of x, k minus 1, would be the height. Let's take a visual and see what's happening here. I hope you can see we've highlighted this in green. If you were to look, we could have our rectangles. We'd always have the same base. That base would be delta x. But the big question that we're going to have is, how do we determine the height? How do we find out how tall that rectangle should be? And you can see right here we might have our curve on any endpoint, any base of a rectangle. If we went with the left endpoint could determine how tall that rectangle should be. And you can see this is what's happening in each and every one of these scenarios. It's that left endpoint, look at this rectangle right here, that will determine how tall that rectangle really is. So we have a base of delta x where heights are always function values. But we'd add up all these rectangles and we'd have an estimate for the area underneath the curve. RRAM, well, it's pretty much the exact same scenario, except what you're going to really see here is that this time, as we look at our individual rectangles, it's going to be the right endpoint for any given individual rectangle. That right endpoint, that will determine how tall that rectangle should be. So you can see consistently for any of these rectangles, it's always that right endpoint that determines the height. What you're always going to have is the area of a rectangle is base, which is always delta x times the height. Add up all these rectangles right here, and you'd have an approximation for the area underneath the curve. Again, we could call that RRAM. And then we move to MRAM. Of course, you could go to any rectangle that you have seen here. For MRAM, it's the midpoint of every subinterval that would determine how tall that rectangle really is. You can find out the base of the rectangle. Again, the base, delta x, like we wrote up earlier, b minus a all over n. You'll know the base of each and every rectangle, but go to the midpoint of any of those subintervals. That'll tell you how tall the rectangle is. You can add up these n rectangle areas, and you'd have this midpoint rule. So over and over again, what we're doing today, plain and simply, we're just going to be finding the area of n rectangles, adding them up, and we will be getting an approximation for the area underneath the curve. I think you can see from these pictures that it really will not be the true area underneath the curve. Take a look at LRAM. I think you can see that our rectangles in this picture are going over the curve. We'd be getting too much area. You know, we just want the gray area to be approximated. Well, add up all those rectangles. Your rectangles are too tall. By way of comparison, look at this picture here for this curve. RRAM. Well, our rectangles are consistently inscribed within the curve. We're getting too little area. Look at MRAM, and for any given rectangle, I think you can see that there'll be some area that you're too short on, but some that you're going to have too much. You might hope that those would counterbalance each other out. They actually do a remarkably good job doing that. We're going to stop here. This is just the introduction of the 3 rectangle approximation methods.